Welcome to Unit 2, Essay Question number 1, Part 1. So first we're going to talk about the neuromuscular junction. And if we remember with a neuron, it's going to send a energy signal or a positive like electric field throughout the neuron. And as it's going, it's going to have action potentials and it's going to open up sodium voltage gated channels, and it's going to continue that until it reaches the terminal. And when it gets to the terminal, it's going to hit a voltage gated calcium channel, and that's going to open up and allow calcium to come from the ECF into the ICF of the terminal end. And that's important because here we have, if you remember, the vesicles that hold neurotransmitters. And the calcium, well, I guess with the neurotransmitter, with the vesicles, they have little arms. They're called snare proteins. And there's snare proteins on the vesicles and also on the membrane. And so when calcium comes, it allows those snare proteins from the vesicles and from the membrane to attach and to pull on each other. And so it pulls the vesicles to the end and allows those neurotransmitters to get released. And then this is the muscle cell, and it's I believe it's an N1 receptor, and it's coming from a motor neuron. And ACH, acetylcholine's the neurotransmitter that's being released. And so the neurotransmitter, it's a ligand. It's gonna connect the sodium, a ligand gated sodium channel, and that's gonna allow sodium to come into the cell. And sodium's gonna do its WONG, its positive electrofield, and as it travels this way, it's gonna open up sodium voltage gated channels. This is kind of a review from last unit, but it's gonna open them up, continue the WONG, and it's gonna make it down. Well, I guess something that's different about a skeletal muscle cell is that we have this right here, which is called a T-tubule. And the reason why this is important, because as you can see, the membrane has like a valley or an alley into the cell, and that's because it needs to be close to the SR, or the sarcoplasmic reticulum, because calcium with muscles is essential, and the SR, or the sarcoplasmic reticulum, is what holds the calcium in the ICF. We know there's also calcium in the ECF, but with skeletal muscle, it uses the calcium from the ICF. And so the reason why we have these T-tubules is so that the membrane can be close to the SR. And that's because we have something called DHP, and that's a voltage-gated calcium channel. And when this has that positive WONG come, it opens it up. Let me slow down a little bit. So yeah, inside the SR we have the calcium, and connected to the DHP is called the RYR, and the RYR is what's connected to the SR. And so when we get a positive WONG, the DHP, the voltage-gated calcium channel, opens up, which also opens up the RYR. And so it's going to look something like this. We're going to have it open. And so we're going to have an opening from the ECF into the ICF, and an opening from the SR that goes into the ICF. So you can see it's like open from both sides. And this is how we get calcium out of the SR into the ICF, so calcium can do what it's needed to do for skeletal muscles. So as you can see, there's calcium in here, but how do we get calcium to get close to here, to come out of here? There's something called calsequestrin, and all I really know about that, it has negative charges, and so it attracts this calcium and brings it in. The calsequestrin is next to the RYR, and so it gathers those calciums close to RYR. So when it opens up, it's already ready to come out. And so since there's a low concentration of calcium in the ICF, we're going to have the calcium from the SR come out. But we also know that there's a high concentration outside in the ECF, but the calcium coming from the SR is so powerful and it's so much that we don't really worry about the calcium coming from the ECF, even though it's a little bit coming in, but compared to this amount, it's so little. So yeah, that's how we get calcium into the ECF. And that's how we get the calcium into the ICF. And the reason why we need the calcium in the ICF is because that's what allows our muscles to contract. And so I'm gonna move down here. But yeah, also too, another thing I should mention is with the SR, we also have the circuit pump that's powered by ATP, and that's what restores calcium back into the SR. Yeah, it's called a T-tubule. Don't know if I mentioned that, but that's what that is. But yeah, we'll move ourselves down this way. All right. And this is where we're gonna get to why we need calcium inside. So, all right. So this is a muscle strand right here. And muscle strands are striated. And that's because they have these things called sarcomeres. And this is a sarcomere up close. This is like what it would look like on a muscle strand. And as you can see, there's those dark spots, and so it's just like striped. That's what striated means. And so these are sarcomeres. This is one blown up. So on the sarcomere, we have these things coming down. Those, I don't know, we call them pillars, but those are Z discs. You have these arms coming out of them. That's called nebulin. But on the nebulin, you have F-actin. And those are those green circles all together. If you take one of those green circles by itself, that's G-actin, but all together, it's F-actin. And then here you have the myosin, and then these little things that hold the myosin are, it's called titin. And yeah, that's kind of the structural stuff. But how it all works is, essentially what's gonna happen is, you know, with a muscle, it contracts, it gets pulled together. That's what's gonna happen to this muscle, and the reason why that happens is because each of these sarcomeres are gonna contract like that. So to explain the contraction, let's move it like this. Okay, so we're gonna take this section right here and blow it up a little bit more. So we have our G-actin. We also have something called tropomyosin. This is that blue, it's kind of hard to see with the light, but it's a blue line, it's a blue protein going along the F-actin. And as you can see, this is one of the G-actins by itself, but on it, on the bottom part, it has a myosin binding site. And all these are gonna have it. So the whole G-actin is gonna have all of these myosin binding sites. And so first we're gonna have the tropomyosin on there. It's gonna be bound to the myosin binding sites. Then we have troponin. And troponin is another protein, and it's gonna have three parts to it. The first part, don't know what it's called, but there's an I there. The next part is the T part, and we have the C part. So the C part's important, and C is for calcium because that's where the calcium binds. and it's gonna have a low affinity binding site and a high affinity binding site. Each binding site is gonna have two places where calcium can bind. The high affinity binding site for calcium is gonna bind there, and that's what's gonna keep troponin bound together. That's what's holding it together. Then it still leaves this low affinity binding site. But troponin, it's gonna bind to the F-actin, and the I part is what's gonna bind to the myosin binding site. And then the T part is what's gonna bind to tropomyosin. And that leaves the C section where calcium can go. So one of them was already gonna be taken up with calcium, but it's gonna leave another binding site available for another calcium to come. And when calcium comes in, if you remember when we talked about down here, when calcium comes from the SR into the ICF, this is where it's going. And this is also all in the ICF. So calcium is going to come in while troponin's bound, and it's going to bind to the low affinity site, and it's going to move tropomyosin, kind of roll it over, move it out of the way, and it's going to open up these myosin binding sites. So I drew right here, you can see calcium came. Let me draw calcium coming. Calcium came, it bound there. Troponin's going to go through it's going to transform, a conformational, transformative thing, and it's going to move tropomyosin out of the way. These binding sites are available, and if you remember I talked about over here the myosin, these binding sites are going to be available, and myosin's going to have a want to bind there, and so it's going to bind up with the myosin binding sites, and it's going to be bound. And going back to here, so the tropomyosin, the blue line, is going to move over and be available to the myosin head, and the myosin head's going to bind. And essentially what's going to happen, it's going to bind, and it's going to go into its uncocked position. This is a cocked position. Uncocked position is going to pull itself closer together, and then it's going to detach, recock again, like that, and that's what pulls the sarcomere together. When you have all these sarcomeres pulling themselves together, the whole muscle fiber is going to contract. When you have all these muscle fibers contracting, that's what's going to cause the muscle actually to contract. But let's come over here to this cycle. Can't remember the name of it, but it's an important cycle having to do with skeletal muscle. So we're kind of just going to blow up this part right here and the stages that myosin goes through when it's pulling the sarcomere together. So right here, we have myosin in its cocked position, and as you can see, it has an ADP attached and a phosphate. So that's how it is when it's in its cocked position, it's ready to go. We talked about calcium comes in from the SR, it comes in, it binds to the troponin. The troponin then moves the tropomyosin out of the way, making those binding sites available. So here, calcium comes in, makes those binding sites available for myosin because it moved tropomyosin out of the way. So myosin's head gonna attach to the open myosin binding sites. When that happens, it's gonna release some heat. Yeah, we still have the ADP and the phosphate. But then once it binds, it's going to have such a connection or attraction here to the myosin binding site that it's going to lose its desire to hold on to ATP and phosphate. So ADP and phosphate are going to fall off. And then we're going to have here, myosin is still going to be attached, but with the loss of that phosphate, it's going to be in this position. So it pulled it together. So it's from here, phosphate fell off. It's still connected to the G-actin, to the myosin binding sites, and it's pulled it together. So now it's uncocked, but it's still connected. So to get it unconnected, ATP is going to come in, and it's going to detach it from the myosin binding sites. Still going to be uncocked position, but it has the ATP on it because ATP came in. And it's going to go through hydrolysis, where ATPase is going to snip off one of the phosphates. And the phosphate's going to go, like where we started, right here, and it's going to put it into its cocked position. And it's still going to have ADP. The phosphate's in cocked position. And now it's ready again to have a calcium come in, free up that binding site with troponin, the myosin binding site, and attach again. And that's the cycle. It's going to continue to go through that cycle. And yeah, it's going to, and then it's stuck, detaches, ATP comes in, hydrolyzes, ready to attach again when calcium comes in. So yeah, that is skeletal muscle. So that's part 1 of this essay. Part 2, coming here in a sec. All right, so this is part 2 of Unit 2, essay question number 1. Okay. We're going to talk about sources of energy for the muscles. There's 4 we talked about in the book. Cytosolic ATP, creatine phosphate, glycolysis, and aerobic or oxidative respiration. I'm going to try not to look at them and just explain them to you. Okay, so what's the first one? I know it. Okay, it's the systolic. This is systolic one. ATP, systolic ATP. So that one is located in the cytoplasm. It's short-lived. It only lasts between like 1 to 5 seconds. Trying to remember what else. It's for like very rapid movement, like with the eyes. And oh yeah, that's what I was missing. Anaerobic. So that means it doesn't require oxygen. The next one is creatine phosphate. Is that right? Yeah, creatine phosphate. Now it's also anaerobic. It doesn't require oxygen. So this one, once the systolic ATP is depleted, it calls upon the creatine phosphate, and there's a kinase that comes in, clips the ATP, clips the phosphate off the ATP, and gives it to the ADP to regenerate some energy, some ATP. And this one lasts up to 10 seconds. It requires the kinase, short-lived, up to 10 seconds. Yeah, so that's the creatine phosphate. The next one we're going to talk about, it's the last anaerobic one. It doesn't require oxygen. And that one is the glycolysis, or glycogen. So this one gets glycogen that's stored within the muscle cell. I think it's the muscle cell. Or it's just stored in the muscle, but yeah, it breaks down and uses the glycogen as fuel or energy. And like we said, that one doesn't require oxygen, and I think this one lasts up to a minute. Yeah, it's sustained for a minute. The last one we're going to talk about is aerobic, or oxidative respiration, and that one can last for hours. It requires oxygen. It comes from the mitochondria, and yeah, it's slower than anaerobic, meaning that it's not meant for like super fast, quick movements, and it's also going to be depleted. Well, it's not. It's going to last longer, so it's not going to be depleted as fast. It uses fatty acids. This one's like for like quick eye movement. I think that was what was mentioned in the book. This one also kind of has quick movements, like if you're just like working out at the gym and you're lifting a heavy weight, you're just not going to last super long. That's kind of what these ones are for. But then once you get here, this is more if you're like standing. In the book, it mentioned the soleus in the calf or in that part of the leg. And those are ones that can just last a really long time. Yeah, they're not going to get fatigued as fast. So yeah, those are our energy sources. Then we're going to come over here for smooth muscle. You can see on the board, this is a smooth muscle cell. It's different from, I guess let's talk about some differences between smooth muscle and skeletal muscle. I'm trying to remember. Smooth muscle, let's see, I just can't remember a ton. Smooth muscle, let's see, took a picture of this. All right. Okay, skeletal muscle connects to the bone and moves the bone for the most part. Smooth muscle doesn't. Smooth muscle or skeletal muscle fatigues for the most part a lot faster than smooth muscle. Smooth muscle is a lot more fatigue resistant. Also another cool thing is it contracts slower but with greater force. That's smooth muscle. Contracts slower but with greater force. There's two types of smooth muscle. There's single unit and multi-unit. If I remember right, single unit, it has gap junctions where, well, also too, it's not dependent upon the nervous system or the endocrine system. It's independent, and so within that muscle itself, it can depolarize and create an action potential, and it will create like a wave throughout that whole muscle until it gets to the end. Whereas with multi-unit, there's no gap junctions. I think what it says is they're not electronically coupled, and they do depend on the nervous system and the endocrine system. I'll have to study that a little bit more. But yeah, so now we're on smooth muscle. This is a smooth muscle cell. Unlike skeletal muscle, there's no T-tubules. And that's because it doesn't have to be, the membrane doesn't need the DPH, the voltage-gated calcium channels, to be connected to the RYR to open. The RYR can open itself with a G protein and with phospholipase that lets in or creates, I can't remember if it lets it in or if it creates it or makes it, but it's IP3, and that goes to RYR and opens it up so that calcium can leave the SR into the ICF. Another thing too is with skeletal muscle, it gets all of its calcium from the ICF, whereas smooth muscle, it can call upon calcium from the SR and also from the ECF to bring it into the ICF. But yeah, talking about ICF, the ways that can bring in calcium. There's ligand calcium channels, there's stretch action calcium channels. There's another one in here that's like calcium, like spark calcium channel. Can't really remember, but there's somehow where there's another little channel within the SR that can let calcium out when calcium activates it. Can't remember that one a ton. But yeah, this is a smooth muscle cell, a little bit different than a skeletal muscle cell. Coming over here, last time we talked about this cycle. Can't remember the name of the cycle for the skeletal one, but there's also the same sort of cycle, similar cycle for smooth muscle. There's two types. There's phasic and there's tonic. Phasic only draws from the ICF, tonic draws from the ECF and the ICF. First, let's talk about phasic. So we still have our myosin head, and we still have, this is a sarcomere, pretty sure. Same thing going on here. Myosin heads right here, cocked, ready to go with its ADP and its phosphate. But with this next stage, it's going to bring in calcium. It's going to bring in MLCK and ADP. The calcium is going to come in, and I'm trying to remember what it does. But yeah, that's why. Okay, calcium comes in. The reason why that's important is because the MLCK isn't activated until there's a little thing, I can't remember if it's a protein or what, but it's called, like, it starts with a C, colmonderum or something. And when that has calcium bind to it, it activates the MLCK. And the reason why the MLCK is important is because it's a kinase, and when this ATP comes in, this MLCK snips off one of the phosphates from the ATP, and sticks another phosphate onto the myosin. So throughout all this, myosin head attaches to the binding site, and then when that happens, it's going to lose ADP and the original phosphate. Those drop off. We still have the one that came from here. Call it the second one. So now it's in its uncocked state, still attached. ATP is going to come in, detach it. I should have drawn the other one on there. There it is. But yeah, it's going to look like this. It's detached, but it can do one of two things. One of the things it can do, it can have MLCP come in, and MLCP is, it's another, can't remember the name of it, but it's another thing that can come in. It phosphorylates. But it can come in and snip off that second phosphate. But with this, it's not always activated. It's only going to be activated during times when there's a lot of calcium, because there's something called rho kinase, and rho kinase, if there's not a lot of calcium, rho kinase is activated. And if rho kinase is activated, it's going to inhibit MLCP. So if it's going to inhibit MLCP, then it's a lot less likely it's going to come and snip off this phosphate. But if there's a lot of calcium, it's going to inhibit rho kinase, and if rho kinase is inhibited, there's going to be a lot of MLCP going around. But in this case, let's just say there's not a lot of MLCP, there's not a lot of calcium, or abundant amount. So it's not going to get snipped off very often. So if it's not going to get snipped off, ATP is still going to hydrolysize, and it's going to turn into ADP and a phosphate and put it back into its cocked position. But this is going to stay on, so it doesn't have to have an influx or doesn't need to receive calcium, MLCK, or ADP. It can just jump straight to here and keep going through. And this is good because it doesn't require these ones as much and can do for a quicker cycle. It can go a little faster. But it's not going to do that forever. Still, every once in a while, it's going to have MLCP come in, and it's going to snip it, and it's going to have to go this route and receive these again and restart, do a few more, and MLCP will come again, and it's going to have to go through this, but it'll do a few more. So that's phasic. But yeah, the important thing, it only draws upon the ICF. The reason why that's important is because when we draw upon the ICF and the ECF, that's where we get tonic. And hopefully that's a little better. With tonic, yeah, draws upon ICF, ECF, and same thing going on here in myosin head. Like in phasic, it's going to have calcium, MLCK, and ATP come in. The MLCK is going to phosphorylate, or it's going to kinase or whatever, and it's going to give the extra phosphate from ATP and stick it on there. But in this case, we're drawing calcium from the ICF and the ECF. So not only are we getting calcium from here, we're also getting it from the outside, the ECF. So we're going to have a high amount of calcium. And if you remember, Rho kinase is inhibited by calcium. But Rho kinase, its job is to inhibit MLCP. So if there's not a lot of calcium, there's a lot of Rho kinase to go around and inhibit MLCP, which gives us less MLCP, which lets us do phasic. But if there's a lot of calcium, it's going to inhibit Rho kinase, which is then going to not let Rho kinase inhibit LCP. So there's going to be a lot more LCP that's available. And if there's a lot more MLCP that's available, number one, it's going to be able to phosphorylate and take off those second phosphates. Because if there's a larger ratio of MLCP compared to MLCK, then it's going to be able to do its job over here, but it's also going to give it the opportunity to come over here and take off this second phosphate even earlier in this phase of the cycle. And if it does that, then these are all going to fall off like normal, but MLCP is going to take the second phosphate off. The myosin head's still going to be stuck there, but it's going to be stuck there with an even greater strength. And because it's not having anything else that it's bound to, so it's going to be able to bind to that binding site even stronger. So hence, this is why we have the blue line, the blue squiggly line, which represents a longer time that it takes to remove this myosin head with the ATP. And so it's staying contracted for longer. It's staying in this uncocked state, or staying in this state longer, holding it there, because this ATP is going to come in, but it's going to have a harder time trying to get it off because it's stuck there so strongly. But eventually it's going to get it off, but it's going to delay quite a bit. Then we'll go into normal hydrolysis. ATP is going to be there. We're going to get that again and go through this. The reason why this is important, this is like a sphincter muscle that can stay contracted for a long time, like your, what's it called, your bladder. Like a sphincter in your bladder, it can stay contracted for a really long time, so it's going to use something more like tonic. And the reason why that's good, because with high amounts of calcium coming from the ICF and ECF, it's going to cut this off earlier, and it's going to have that delay to get that myosin head to detach. from the myosin binding site. So that's part 2. This is part 3. And we're going to talk a little bit about spindle apparatus. These are important because they detect stretch. We have a chain fiber and a bag fiber, and those are found within the muscle itself. Chain fiber, it's long. Spindle fiber kind of has this belly right here. And what these are gonna do is they're gonna like be taut all the time. They're gonna have tension on them all the time. So when the muscle stretches, they're gonna be able to feel that tension, or that stretch, I mean. But also, when the muscle contracts, they're able to use these static gamma and dynamic gamma to move in to still keep it taut. So it can, because if it's loose and there's movement, it's not going to be able to, it's going to be, I don't know, loose, and it's not going to be able to detect the stretch. But since it has those gamma ones, it's able to move in, always stay taut, so it's always able to feel whether, feel stretch or not. But yeah, there's type 2 and type 1A sensory innervation. Type 1A is bigger in diameter. They're both myelinated, but type 2 is bigger, so it's gonna have like more rapid, quick signals. Type 2's also myelinated, a little bit smaller in diameter, so it's a little slower. But yeah, the important one, chain fiber, detects or senses how long, or the time of the stretch, the duration, whereas bag fiber is the rate, like how quickly it's stretching, how quickly it's stretching. This is for how long it's stretching for, over a minute, 2 minutes, 10 seconds. Whereas this one, it's like how quick it's happening. Both are important. So this is going to bring us into a couple of reflexes. One of them is the stretch reflex. I might just talk about this. I don't know if I want to draw it. I'll draw it. So let's say with the quad, if we're gonna extend the leg, extend it. The quad's going to contract. But if we bend the leg, it's going to stretch. So, like we talked about those spindle apparatus, if it detects stretch when it's not wanting to or involuntarily, it's going to detect it. It's going to come into the spinal cord, and it's going to say, hey, we're getting some stretch. And it's going to do one of two things. It's going to do two things. It's going to connect or send a signal to I think it's a motor neuron, to quads, and it's going to say to contract. It's going to send an EPSP to contract. It's stretching, but it doesn't want to stretch, so it's going to contract and keep it from stretching more. But also, it's going to send another EPSP to an interneuron, I think is what it is, and that is going to send an EPSP. This one can only send EPSP. So it's going to send EPSP, excite the quads to contract. But if we want the hamstrings, we don't want them to keep on contracting because that's what's stretching the quads. We want the hamstring to stop contracting. So it's going to send an EPSP to this interneuron, which is going to send, it's going to translate it pretty much or change it so it becomes an IPSP, so it inhibits the hamstrings to stop contracting. And so that's the stretch reflex. We also have a Golgi tendon organ reflex, and that one's a little different. That one has fibers or like has sensory stuff within the tendon, and that senses tension. And so let me erase this real quick. So let's say you're lifting something really heavy. Muscles are strong enough where they can hurt your bone, rip it off, break it. So let's say the quads, you're like deadlifting, you're trying to lift something up, and the quads are really contracting, and you're lifting a lot of weight, and the sensory here is like, hey, this is too much. We're about to hurt ourselves. So it's gonna send a signal, and it's a little different than the flex one because in this case, it's gonna send an EPSP, an excitatory one, directly to the hamstring, and it's gonna tell the hamstring to start to contract. Because I'm trying to lift, it's gonna start to contract so it pulls me back down. But it doesn't wanna fight with the quads because that's gonna be a lot because it's flexing really hard. So it's gonna send an EPSP to the interneuron, which is gonna take it and turn it into an IPSP. So it takes it, goes to the quads, IPSP inhibits, kind of turns off the quads. So they stop contracting, now they relax. My hamstrings are receiving an EPSP to excite, so it stops that to release the tension. The last one is the withdrawal. I'm just gonna stand here to explain this one. So this one pretty much does the same thing that we talked about here on one side, but the opposite side does the opposite of that. So let's say I'm going to touch a hot stove. It's really hot. I start to pull back. My back muscles are exciting, or they're contracting, whereas from that sensory of the hot stove, it's sending a signal to these muscles where the ones in front are going to get IPSP. They're going to relax to keep me from pulling forward or leaning forward. But the one is going to send signals for the EPSP to the back to excite them to move back. But at the same time, the opposite, the front side is going to be receiving, of my left side is going to be receiving EPSP to pull me forward on this side receiving IPSP to relax, to allow my back side to receive ESP on the right to pull back, whereas on the left side, receiving EPSP on the front to pull forward, whereas the back on my left side is receiving IPSP to allow me to relax my back side to let me come forward on my left side. That makes sense. But yeah, one side pretty much receives one, and the other side is just opposite of that. So it can have something like this, or if I'm starting to fall, or if let's say I step on something with my foot, I'm gonna pull up with my right leg. I'm gonna pull up. Let's say I'm walking, step on something, ow, pull up. Quads are, let's see. Yeah, quads are contracting to pull up. So they're receiving EPSP. Hamstrings are relaxing, receiving IPSP. But on this side, my hamstrings are contracting and my quads are more so relaxing because it's taking that weight. My leg wants to stay straight. So my hamstrings are allowing it to stay straight. So yeah, that's those. That was part 3, Unit 2, Question 1. Thanks for watching. We'll be back next time for part 2, Question 2.